webinar series in partnership with Enerchange, and I'm filling in for Jochen Schneider, who cannot join us today. I'm very pleased to have with us today Bastien Hermant from TLS Geothermics in France. Bastien is the R&D engineering geologist for TLS, started work with the company in 2017, and is based in Toulouse in the southwest of France. And with that, I just kind of jump over to Bastien. Bastien, the floor is yours.
Hello, everyone. Thank you, Alexander, for this brief introduction. So today I will present you the magnetotelluric exploration of crustal fault zone geothermal system in the French Massif Central. So I will begin by defining what is a geothermal, a deep geothermal system, and specifically what we call the crustal fault zone geothermal system. Then I will talk a bit about the geothermal potential of the French Massif Central and the geophysical method that was applied for the exploration of this area and the specific geothermal prospect of TLS Geothermics in this area. And I will focus on the magnetotelluric exploration of the SURE license, meaning the survey and the different results we have. But first, who is TLS Geothermics? So TLS is a French explorer and developer of deep geothermal energy for electricity, heat, cold, and mineral production. So we have a dedicated expertise for deep geothermal energy, and our work cover all the steps of a geothermal project, from the feasibility studies to the project development through a dedicated exploration process. We are currently several people working for TLS Geothermics, and we have a project portfolio comprising 3 licenses for high temperature geothermal exploration in the French Massif Central, in partnership with Storengy from the NG group. And we also have 5 additional license demands in the French Massif Central, but also in French overseas. And we are currently looking to some opportunities internationally. TLS Geothermics is very active in research and development in all the field of geoscience, including geology, geophysics, and geochemistry. But we are also active in machine learning and the modeling of geothermal systems. And all these aspects of research and development are in partnership with universities in France, but also internationally through research projects. So now let's talk a bit about what is a deep geothermal system. We used to make the comparison between geothermal system and petroleum system because petroleum system is defined by key elements, and if one of these elements is lacking, there is no possibility of having a resource. So in the case of petroleum system, we need a source rock from which the hydrocarbons are generated. Then these hydrocarbons migrate to the reservoir where they can be stored thanks to a seal, which is the last main element of this petroleum system. And now if we compare it to the geothermal system, we also have 3 key elements. So the first one, which is the main one, is the heat, because the heat is what we are looking for, is the energy of the system. But we also need fluids, which are the vector of transport of the heat. And we also need drains to allow the fluids to circulate into the system. If we are talking about a convective geothermal system, or a reservoir where fluid can be stored if we are looking at a conductive geothermal system. So we have these 3 parameters, these 3 elements, and we want to define 2 parameters, which are the temperature and the fluid flow that that could be reachable and by this system. And these two parameters define the heat quantity of the system and therefore the geothermal resource. So our objective is to reach a natural drain or reservoir where hot fluids are circulating. Now, if we focus on the crustal fault zone geothermal system, which is a favorable concept with a high potential of replicability, if we look at the three key elements, the first one, which is the drain, in this concept, the drain is, which is also the reservoir, is a large fault zone deeply rooted in the brittle ductile transition that induced a dense fracture network and therefore permeability, even very deep, and some specific favorable structural setting, such as the fault intersection or a fault step over that focused the fluid circulations. Then if we look at the heat, in such a system, the heats can come from the radiogenic rich basement rocks, because the crustal fault zone are usually in basement rocks. So the heat comes from the radioactive disintegration. But the main source of heat is the fluid kinematic into the permeable network, into the drains that induce heat convection and therefore heat anomalies at lower depths. And additionally, there could be a potential volcanic or plutonic activity that give an additional amount of heat to the system, but it's not necessary to have an economical system. And then if we look at the fluid, in the case of crustal fault zone, they are usually meteoric fluids infiltrating the fracture network and potentially stimulated by the topographic gradient. And there could be also a mix with a magmatic or a mantelic fluid, depending on the area and the activity of the area. So now a bit about the French Massif Central. So the French Massif Central is located in the central part of France, and it is a large favorable area for deep geothermal for several reasons that follow the three main elements of the geothermal system. So the first one is that there is a large amount of heat in the French Massif Central due to the mantle rising, inducing a high topography that you can see on the topographic map, and a thin crust and a low bouquet anomaly. That induce also a very high heat flow that you can see on the heat flow map of Europe. And also as a consequence, there is a recent volcanic activity in the area. The French Massif Central is mainly composed of basement rocks crossed by large fault zones. So these rocks are naturally impermeable, but thanks to the large fault zones, there is a fragile deformation and therefore fractures that induced potentially deep permeability. So that's very interesting for a geothermal system. And finally, if we look at the fluids, we have several indications of active fluid circulation throughout the region. So the main one are thermo-mineral springs up to 99 Celsius degree. But there is also a large mantle CO2 flow in all the region and specifically along the main fault zones. In this area, TLS Geothermics is developing a geothermal project in partnership with Storengy in the Sud license. So here it is a crustal fault zone geothermal system. And in our case, we have the main drain, which is a north-south crustal fault zone of more than 50 kilometers long and 3 kilometers thick. So you can see it on the geological map. And there is also an important fault intersection with another direction, which is northeast-southwest. You can also see it on the geological map. For the heat content of the geothermal system, it comes from the heat production of the granite in red in the geological map, which is very high, and also potentially from fluid circulation into the fault zone that induce the anomalous heat flow data we have measured into the fault zone. And additionally, there is also the recent volcanic activity of the Chaîne des Puys. You can see it on the geological map in blue, in the eastern part. And this recent activity could potentially induce a residual magmatic chamber in the crust or in the bottom of the crust that could add heat to the system. For fluid, we also have some evidences, such as thermomineral springs in the fault zone, which are not very hot, but which highlight a deep circulations. And we also have a lot of Mantelic CO2, especially at the intersection of the two main fault zones we are targeting. Now, if we talk about geophysics, which is the main topic of this presentation, some methodologies could be applied to this geothermal system in basement rock. The first one we could think about is seismic reflection, but in our case it was not performed, and it wouldn't be interesting because we are located in basement rocks without strong variations of seismic wave velocity. And seismic reflection has a low capacity for imaging vertical structures, especially in basement rocks where the seismic wave velocity are quite high. We also have a lack of deep well to match the potential seismic reflection data with a 1D velocity model. And finally, this method has a high cost. But we perform seismic tomography, which is efficient for imaging large to medium wavelength anomaly of velocity. This method has a low cost, but it's source dependent. So it's interesting to image at the scale of the crust, but if we want to look at the reservoir scale, it's more useful only as a complement. We also have some gravimetric data, so it's interesting because there are some variation of density in the basement rocks, so we can image large objects with influence on the gravity field. But one limit of this methodology is that it is a potential method, so with the gravimetric data alone, we can't build a 3D density model. We need to invest jointly this data with other data. I will talk about it a bit later. And finally, we perform magnetotelluric surveys. So that's the topics of this presentation. So let's focus on it. So magnetotelluric measured the natural variation of the electric and magnetic fields. So solar winds induce currents in the high atmosphere, and these currents induce themselves currents into the subsurface. And the intensity of this current into the subsurface depends on the electrical conductivity or resistivity of rocks. So that's what we are measuring. So to do so, we need an empty station, which is mainly composed of 2 magnetometers to measure the magnetic current, 2 pairs of electrodes to measure the electric currents, and an acquisition unit. So at the end, the electric conductivity of rocks that we measure is influenced by ion transport. So it allows us to highlight smectite, partial mating, or geothermal fluid, what is very interesting for a geothermal explorer, but also electron transport that could highlight metallic deposits or graphite. After measuring the data, we need to process the inversion of the data to build a 3D model of resistivity. So in fact, we are measuring the impedance tensor, which is a frequential function of electric and magnetic field, and with the large frequencies that are consistent with deep measure. So longer, it means that longer you let your station measuring, larger will be the frequency you measure, and deeper will be your image. So after measuring this data, you need to put it into a grid for inversion. So in our case, the grid is go down to 35 kilometers depth, but you can go deeper. But the layer thickness is increasing with the depth. The inversion of the resistivity model was performed by Imagir, which is a French company specialized in magnetotelluric inversion, and they performed a true 3D inversion. It means that it's not a 3D interpolation of 1D solutions. And to do so, they used the diagonal and the anti-diagonal terms of the tensor to find the best solution, so the best model to fit the data. Now, in the SEUL license, we perform several MT surveys with the idea to increase the resolution as an exploration process. So the first survey was in 2015 with 45 stations covering a large area that you can see on the map with the blue squares. Then the next year, we performed a complement of 4 stations along the west-east transect of the license to test and develop the joint inversion process. I will talk about it a bit later, but the idea is to jointly inverse gravimetric, seismic, and magnetotelluric data to improve the model. And finally, we performed a last survey in 2017 with an additional station in the center of the area to build a high-resolution model, and on the borders of the area, so to the north and to the south, in order to build a new large-scale model, more robust than the previous one. So we have a total of 67 magnetotelluric stations, which is a lot in France, I think, particularly in the French Massif Central. So now I will present you 2 of the models, of the resistivity models we have on the area. So this one is the regional model, so the last one we built. You can see that it is rotated, so it has a specific azimuth. It was to improve the quality of the model, so the fit of the model with the data. But even if it is rotated, you can see in the central part of the model a clear north-south oriented conductive anomaly, which is in fact located along the main fault zone we are targeting. So here at 1,300 meters depth. You can also see it on the crosscut on the left. And if we go a bit deeper, so at more than 5,000 meters depth, you can see a large conductive anomaly in the central part of the model, not clearly oriented along the north-south fault zone, but a bit oriented along the other main fault of the area. Now, if we focused, and you can also see on the crosscut a large conductive anomaly, very deep at more than 20 kilometers depth. Now, if we focus on another model, which is a high resolution model, so corresponding to the white square on the map. So here it is. So once again, we can see a large north-south conductive anomaly, once again along the main north-south fault zone. organized in two parallel conductive anomalies. You can see it on the map, but also on the crosscut, showing that this anomaly is very steep. And if we go a bit deeper, so at 2,600 meters depth, there is here one large conductive anomaly, which is well constrained by the north-south trend of the fault, but also by the other faults, so oriented northeast, southwest. And what we are targeting with our exploration well is to cross-cut all the conductive anomaly, so the shallow one, and to go at the bottom of this anomaly in order to reach what we think will be the top of the geothermal fluid circulation. Now, if we compare this model, so here it's the high resolution model with other data, we can see a strong consistency between the magnetotelluric model and the structural network, which was built completely independently. So very shallow, you can see that the conductive anomaly are clearly consistent with the north-south structure. And a bit deeply, the anomaly are well constrained by both north-south and northeast-southwest fault zone. So the two main fault zones that we are targeting and their intersection. So it means that hydrothermal alteration, so the smectite and the fluid circulations are located and constrained into the fault zone and their intersection. Now, if we go back to our conceptual model of crustal fault zone, you can see here a very deep anomaly, but intracrustal anomaly that could be interpreted as the residual melt from the magmatic chamber of the chaîne des puits. So you can see it on the magnetotelluric model on the left, and on the right side you can see a numerical modeling, so thermohydraulic numerical modeling performed by Duviquet et al. Of the thermal anomaly. So here we have a thermal anomaly due to this residual melt. And what is interesting to see is that this thermal anomaly and the fluid circulation into the fault zone induced a thermal anomaly very shallow into the fault zone that is confirmed by the magnetotelluric data. So you can see here what I said just before, the shallow anomaly, which is constrained into the fault zone, and that we will target with our exploration drilling. What is important to know is that empty data are very interesting, but for the exploration, you need to compare it to other data, such as seismic or gravimetric data. And to do so, we develop at TLS Geothermics a joint inversion process to jointly inverse the ambient noise tomography, the gravimetry, and the magnetotelluric, with the idea to build a more robust model and also to build a 3D density model, which is not possible with gravimetric data alone. So you can see on the right the seismic wave velocity model and the density model from this joint inversion process. So one thing you can see on this model is what we interpret as the brittle ductile transition between 6 and 8 kilometers depth, in which the crustal fault zone, the north-south crustal fault zone, is rooted. It's also a help for us to cross-interpret the magnetotelluric data and to better interpret the conductive anomaly. I mean, we can know if a specific conductive anomaly has a high density or not, and it helps us to choose between, for example, partial melting or metallic deposit. So what next about the project? So now the project, the following step of the project is the exploration drilling that will begin in autumn 2022. So save the date. It will be a deep well of 2,500 meters depth in true vertical depth, with objectives of between 150 and 200 Celsius degree and 100 liters per second of fluid flow. And if it is a success, there will be a second drilling and the building of a 6 electrical megawatt geothermal power plant. And we also have the possibility to drill a second doublet in order to increase the production to 12 electrical megawatts, depending on the measure we will perform into the first drilling and on the power that could be possible to reach with this geothermal system. And finally, this first project in the French Massif Central will be the demonstration of the crustal fault zone geothermal system. And because this conceptual model of geothermal system has a high replicability, it will be the first one of potentially other one in the same area, because there are other crustal fault zone in the Sud license, but also in other parts of the French Massif Central, which is a large favorable area for geothermal energy, and potentially in other parts of the world, because crustal fault zone can be target in a lot of area in the world. So thank you very much, and do not hesitate to ask some question about the presentation and the project.
Thank you so much, Bastien. Very, very, very interesting. And I actually have myself a few questions here, but I would like to go through some of the questions. So if there are some questions in the audience, you can ask them in the question bar. We'll try to go through this. And maybe kind of starting off the bat here, I can't promise I will structure these questions in the best way forward, so stick with me.